Welcome back. Hopefully this lesson has been going well for you so far. So let's take a look at 4-35. Again, hopefully you've already completed past this point. You should have completed the lesson, just now coming back here for a summary. So I'm going to assume you've done these problems already. If you haven't, pause now, go back, work on them, and then come back to this video. So we're taking a look at 4-35, where Tiana, Maylin, and Eddie, and Amy are all looking at this triangle, trying to find the missing side length. So let's see what they all have to say about that. So Tiana says, hey, we can rotate the triangle so 18 degrees is our slope angle, and then our change in y is 4. Will that work? Well, yeah, it'll work. We just have to take it and rotate it around so that 18 degrees is in the bottom left, that 90-degree angle is in the bottom right, and then 4 is my change in y, my vertical line, and a is my change in x, my horizontal line. Well, Maylin says, well, I see it differently. I can tell change in y equals 4 without turning the triangle. How can she tell? Well, if we look at it, if you kind of imagine what this would look like, if you could tilt your head to one side, you can see that, well, the change in y is always the side that's across from our angle, across from 18 degrees in this case. So if you think about it, kind of like if you imagine a flashlight sitting right at that 18-degree angle, and you turned on the flashlight or a laser pointer or something, which is the side that's going to be shining light on? Well, it's not going to be shining light on A, it's not going to be shining light on the hypotenuse, it's going to be shining light on 4, and that's the way I kind of think about it. You can actually imagine this as like a side view of a beam of light coming out of a flashlight, and it's shining on the wall made by 4. So 4 is my change in y, and no matter which way I've had this rotated, that's still going to be the case related to 18 degrees. Yeah, we can take the whole triangle and rotate it horizontally so we can see it all, but we can kind of just visualize this now. Well, then Eddie replies, well, what if we use 72 degrees as our slope angle? Then 4 is our change in x. This is what is he talking about? Well, we can take this and we can flip it entirely around so that 72 degrees, that third angle up there, we haven't solved for yet, but if you use the triangle angle sum theorem, you should find that that third angle is in fact 72 degrees. If you use that, then instead of 4 being my change in y and a being my change in x, it switches. Then 72 degrees is my slope angle, a becomes my change in y, and 4 becomes my change in x. And if you solve this problem with both of these, if you solve this problem using the slope ratio of 18 degrees and solve it using the slope ratio of 72 degrees, you should actually get the exact same answer for a. Either way, you should get the exact same answer. So no matter what we use for this, either way we should get that a is 12, because we either have that with 18 degrees we have a 1/3 ratio, 1 over 3, which would correspond to 4 over a, or we use 72 degrees and we get a 3 over 1 ratio with a over 4. Either way, the ratios are still matching up with the same sides. 4 always matches up with the 1, a always matches up with the 3, just changes which way the fraction is facing. So that basically tells us that, well, if you think about this, it doesn't actually matter which way the triangle is facing. And actually, if you think about it, this isn't a slope triangle, now that we think about it. It's just a right triangle. A slope triangle is a triangle drawn on a sloped line on a graph, and we don't have a graph here. In fact, we just have a right triangle that's kind of been rotated in a weird direction. And that's kind of the secret of what we've been doing. Last couple problems you did, last couple days even, we haven't really worked with a true slope triangle. We've just been working with right triangles. And the secret is, it still works. Everything we've been doing so far still works. It does not have to be just on slope triangles. It works on right triangles too. Because we're not really comparing slope necessarily. We're not comparing like change in y over change in x. We're comparing the lengths of two sides of the right triangle. We can call this side, this 4, we can call this the opposite side to 18 degrees, and we can call A the side next to 18 degrees. So 4, if you think about it, it's opposite from 18. It's across the triangle from it. It is, again, if I use the flashlight metaphor, if I was shining a flashlight from 18 degrees, 4 would be across from it. Whereas A is actually touching 18 degrees. The bottom side, or the bottom end of the line measured A, is actually part of what makes up that 18-degree angle. So it's touching A, or touching 18. So we would call A, maybe the side next to it. There's actually a word for that that means next to, which is adjacent. And so we would say A is the adjacent side, which is going to be more useful language in the future. So we're going to start thinking about that instead. So instead of thinking about it as, change in y over change in x, rise over run, we're going to start thinking about it as the side opposite over the side adjacent, or next to the angle. And if you want to keep thinking about it in terms of change in x and change in y, that's okay. but really try to start thinking about it with this opposite over adjacent, because that's going to come up a lot in the next chapter. So that brings us to our main takeaways for today. I know, already done. That's because this is half a lesson. I didn't want to overwhelm you with new information, so we've just got these two main takeaways. First one, the Leaning Tower of Pisa is safe. We don't have to worry about it falling over. We've got an 84-degree slope angle. It's close, but not at the danger zone just yet. The second thing is that we've actually been doing work on right triangles all along. It has not just been restricted to slope triangles. We can expand this to any right triangle. At some point, we just stopped working with slope triangles, and this started applying to all of them. Still works the same, though. And remember, right triangles is still important. This does not work on any triangle, only right triangles. So that's key. Works on any right triangle, but it has to be a right triangle. You need that right angle in the corner. And if you didn't see them yet, here are the answers to 4-34. So if you want to go back and check your work on those, go ahead. This is a really good place to check your understanding for the chapter so far up until this point. If these aren't making sense to you, stop by that Google Meet that I have up right now. Email me if you're watching this after class time. Double check with me, because tomorrow is the day. Tomorrow is the day I show you the secret. I unveil to you how to do this and how to do it on your own without having to memorize tables, without having to memorize these. You're going to be able to convert angle and slope on your own, by yourself, without my help, but you gotta understand these fundamentals. If you don't have these fundamentals, it's gonna be a little rough for you. So, if these answers do not make sense to you, stop by Google Meet, email me, ask for help, talk to each other, because you need these fundamentals before we can move on to part 2 tomorrow, alright? So, get to work. Hopefully this made sense, and again, if it didn't, ask for help. I'm always here to help. Alright, have a good rest of your day, everybody.